Hi, I'm Matt, this guy, and I'm going to talk to you about geospatial analysis in the cloud using PODPAC and JupyterLab, building upon a lot of really good open source tools. So, a brief introduction about the problem. So, as earth scientists, you need to wear a lot of different hats in order to get science done. And you need custom solutions at multiple different levels of abstraction. So first you need to know the name of the data set that you want to use for your work. You need to know how it's stored, how to get the data, how to read the file type, how to interpret the data, what are the coordinates, what geospatial reference system they are. Lots of different things you need to know for each data set. There are some standards that are emerging that are being very helpful, but it's our opinion that there will always be some data set where somebody's trying a new standard or it's a new instrument that doesn't fit the standard. And so there'll always be some kind of custom data handling that you'd have to do science. We've talked quite a bit to the SMAP scientists, and they all have their own scripts to download and parse the data. And that's just crazy. We should have a centralized way of accessing these data sets in a nice way so that we can get to the science faster. The next level is harmonization. It's great working with just a single data set, but what if you want to compare something like a remotely sensed soil moisture, such as the SMAP soil moisture active passive sensor, to a Cosmos sensor, which is a in situ sensor with kind of a wide footprint, works like a weather station. It's more point data, time series at a point versus spatial data once a day. So how do you compare these two data sets? Well, you have to do some interpolation, maybe some regridding, some subsetting. And so there are a lot of great tools out there to do this, but you have to figure out how to use them for your problem. And then there's this other layer of actually getting your installation working on the machine that you're working on, getting all the dependencies installed, your IDEs. If you want to work on the cloud, which will become more and more important in the future, you have to figure out your cloud deployment and your cloud provider. So there's a lot that needs to happen before you can do science. In comes PODPAC. So one of the motivations for PODPAC is to abstract these different layers. And we do that by writing once a way to interpret these data sets, interpret, read, fetch these data sets. There's a lot of gotchas that a lot of people run into. For example, some data sets store the data at the center of a rectangular cell. Others store it at the top left corner. A lot of details like that they have to be aware of for a particular data set. On the harmonization side, we're glue for a lot of very good open source interpolation functions. Such as we use raster.io, we use PyProject, we use Xarray, SciPy. And so we have an interface to write your own interpolators, but once we understand the data, we can do this automatically to harmonize two data sets together. And then we also provide turnkey deployments. So for Windows, you can download a big zip file, unzip it in a folder, and run. All the dependencies are there. Mac and Linux is a little bit easier to use Anaconda and pip installs, so we don't provide that for those platforms. And we also make cloud deployment on AWS very easy, as I'm going to show during this presentation. Okay, so kind of in summary, PODPAC's aim is to help earth scientists access data in an easy and unified manner, help them to harmonize the data automatically, and then take their analysis and transition it to the cloud with not a lot of pain and effort. So for the rest of the talk, I'm going to give a live demo on a pre-recorded video. And then I'll show you a demonstration application that's built on top of the PODPAC technology. Then I'll give you a sense of where we're going next and just summarize. Okay, so this is my work case study for this presentation. So imagine as a scientist, I want to study vegetation on slope terrain in my local region. And I want to figure out where I should go to do this study. So for that, I'll need terrain data, and I'll need some sort of vegetation index and a way to visually explore the data. To do that right now, without PODPAC, it's quite a lot of work. You need a lot of knowledge in each of these areas. Okay, but let's say that you spend the effort to learn PODPAC. This is how you would do it. We start by creating some coordinates. Now, we've done a lot of work in PODPAC in this coordinates object. It's very flexible. So these coordinates describe a grid. So this is a 101 by 101 by 1 grid. It could be multiple dimensions in time as well, but I just have one time point for this example. But you can also create points, for example. We call these stacked coordinates. So now latitude, longitude go together. And so each point is described by a latitude, longitude point. But for this particular example, I actually do want a grid. Okay. So let's visualize that. This is the area I'm looking at. I'll zoom out a little bit to give people a sense of where this is. And to display that, I'm using SciPy Leaflet, fabulous library. With just a little bit of math on those coordinates that I created. Okay. So, number one, create some coordinates to test what we're going to create on. Next is to set up access to the data sources. So in these 3 lines, I'm not actually doing anything. I'm just creating an interface to these data sets. And this is a unified interface. Each of these are stored in tile structure. So you have to understand the tile structure to really access the data in any meaningful way. So terrain tiles is this grid elevation tiles freely hosted on AWS on the cloud. And MODIS is a NASA instrument measuring reflectance. So there are multiple bands. We're going to be using the red band and the near IR band for this demonstration. So now we have data sources, but we need to do some processing on these. So to process the data source, this is the first time PODPAC actually does anything. It goes up to the cloud. It downloads the data. It puts it into an X-array. So this is actually derived from an X-array data array. We add a little bit of serialization functionality that we need on top of it, but it's essentially an X-array data array, so you can do a lot of nice X-array functions with it. But we download the data, we plot it, so now we can see what our terrain looks like in this region. And so notice that the native coordinates for this terrain tile is nothing like the coordinates that I've specified. So these coordinates are in WGS 84, latitude, longitude coordinates. The native coordinates for this data set is in spherical Mercator or Web Mercator. This means nothing to me. So I'm going to transform it to a coordinate system that I know. And so you can see that we're asking for coordinates that are a subset of a single tile in this particular case. And I'm actually sampling it maybe roughly on the same resolution as the original data set. Okay, so next, let's do some processing on it. So I want to compute the slope. And for that, I'm going to use a spatial convolution and then an arithmetic algorithm. So first, I'm calculating the slope in X. I say that the source is the terrain data, and I specify a kernel. So I'm just going to take the difference between basically a central difference. And I'm not worrying about normalizing by the actual spatial extent. And we'll talk about that a little bit later. Do the same for the Y. And then this is a very nice thing that PODPAC lets you do, also with other data sets, is you just specify the data set, and then you combine it in a very simple way, A plus B way. You don't have to write code to do interpolation or regridding. This happens to be the same data set, but I could put MODIS in here, for example, as well, and the same equation would work. I'm adding some style information that we'll use later, and then we'll evaluate it and actually plot it. So here's the slope for the terrain that we had. And so because I want to study sloped areas, I actually want to mask it. So arbitrarily 30 look like a good value. We can try 50. So that's masking it a little bit too much. I think 30 was a good value. So now I can focus on only these areas that have high slopes. So I've got my terrain piece. I can now mask out areas that do not have a high slope. So the next step here is to do some computation on MODIS. First, I'm going to calculate the normalized difference vegetation index. So it's just the difference between the near IR and the red divided by the sum of the two. And again, I'm doing some styling here. So we'll again evaluate it at the arbitrary coordinates that I've specified. This goes, again, downloading the data from the cloud, figures out how it's stored, and downloads it to my local machine and plots it for us. Okay, so now we've got the processing on each of the individual data sets. Let's combine them. In this case, I'm going to combine them just by making a mask. So the source data is going to be this vegetation index. I'm going to mask it based on the slope. And anything less than that limit that I specified, I want to mask that out. So that's what's going to happen here. So again, at this point, we haven't really done anything. If I haven't done any evals before, it would have been very fast. But I'm testing here. I'm working interactively. I want to see what this looks like. So I'm going to eval and plot it. And so that's what we have. But the really valuable piece is this JSON that we've created. So let me just print the raw version of it. So this really describes the full processing pipeline. So what we've done up to this point here. And let's look at that a little bit. So this is the terrain tiles. This is the PODPAC node it uses to access the data. We can look at the convolution. You can see it takes this terrain tiles as an input, and then it defines the kernel here. We can look at this arithmetic function. So as inputs, it's going to take the two spatial convolutions that we've had, and then it's going to use this equation to combine them. For MODIS, it's similar. Again, we have these arithmetic to combine the near IR and the red. And then finally, the mask takes the two arithmetic functions and combines them to give the mask display. Okay, just to give you a sense of how that JSON is defined. Okay, so that was great working on my local desktop, but I really want to do some of this on the cloud so I can take advantage of the parallel processing and the processing power available on the cloud. So now I'm going to set up a new Lambda function, which is a serverless technology, to run the same pipelines. And this little cell here I took from this notebook, which describes the process of setting up AWS Lambda functions in more detail. Basically, you have to specify some settings. So you need some access keys. These are credentials. Then there are some general settings. You can set up a budget, tags for tracking various things. I'm going to be using a couple of these below to create my Lambda function. And here's more details about credentials. So if you want to come back and run this notebook after this talk, this will hopefully give you enough information to set it up and have it work on your machine. So I'm going to increase my log level a little bit so we can see what's going on behind the scenes. What I'll be doing here is creating a new S3 bucket. This is the name of the S3 bucket. This has to be globally unique. So if you try to use this on your own, it might not work. I'm also going to create a new Lambda function. This will be its name and a role to manage permissions between the various AWS resources. Next, I create a PODPAC Manager Lambda, AWS Lambda node. So this is a great node. Managers in PODPAC are used to manage how nodes are processed and where they're processed. So other things you'll find in managers are parallel processing nodes or multi-threaded nodes. In this particular case, this node helps run pipelines on AWS using serverless Lambda functions. So for this particular node, I'm going to be using these settings that I've specified. In terms of triggers, I want the AWS Lambda invoke trigger and also an API gateway, which will give me a RESTful API, which we've actually we use it for a WMS, a lightweight WMS server. And then in order to make all this work, I need to specify a couple of environmental variables for the Lambda function. This line is needed because I'm working on the development version of PODPAC. If it was one of the releases, it shouldn't be required. And this piece I need to get past a security feature. So this actually skirts the security feature, which is not recommended. But while I'm developing, it's helpful to be able to do something like this. Okay, so now I've created this node. The describe tells you exactly what you're going to be creating on AWS without actually having to do it. So there are a couple of defaults which you can also change. I'll highlight the timeout. So Lambda functions have a maximum of 900 seconds of compute time. By default, we only use 10 minutes. And by default, we give you 2 gigabytes of memory, which I think is the maximum. We use some tags to track our budgets. And then down below here, there's some default budgeting information. So this won't limit the Lambda function from running, but it'll send you an email once you start hitting this budget number. So I've been running this a couple of times. So first I'm going to delete the existing functions, and then we'll just rebuild it from scratch. So this line doesn't demo very well in terms of all the amazing things it does. This lets you build the resources, the cloud resources you need without actually knowing the details. It sets up all of the nitty-gritty permissions that you need for the various components to work together. It takes a Lambda function distribution that we've built for PODPAC specifically. It downloads it and it executes it to build the Lambda function. And then also here, I'm grabbing the RESTful API node that was created for me. And so you can see this wonderful URL that's been created for me to evaluate the function. And then I can test it. So here I'm taking the same Lambda function, Lambda manager node, and I'm specifying my masked NDVI node as the source. I'm evaluating with the settings that I specified above. And this eval actually runs on the cloud. So on AWS, it spins up a server for me. It downloads the data for MODIS and the terrain tiles, and that happens in the same data center, so that should be pretty fast. Then it does a computation, and it sends back the results to me so that I can plot it. And this is exactly the same output as we saw up here. So they compare pretty well. So exactly the same thing that you are running on your desktop, you can run in the cloud with not too much effort. Okay, so now I have access to 1,000 compute nodes on demand for 15-minute intervals, which is amazing. So I can do huge parallel computation if I wanted to. But I also have a lightweight WMS service, so I can interactively explore and share my analysis. So let me demonstrate that. I'm going to look at the MODIS red band. And so what I'm doing here, actually I want the MODIS red, is I'm using SciPy leaflet again. I'm creating a WMS layer. I'm using that API URL that I saved from when I created the Lambda function. And then I'm specifying the JSON as part of the URL. And so PODPAC will parse the URL, rebuild the pipeline, and do the computation on the Lambda function. So now I can interactively explore this MODIS red channel. Same with the terrain data, for example. And this is just exploring the raw data sets. Again, we can do this interactively. But we can also explore pipelines. So this is my slope pipeline. And if I was debugging this, for example, I can start zooming in and I'll notice that the magnitude changes. And I realize I really should have normalized by the distance that I'm looking at. But this is a really, really helpful tool to interactively explore the data that we have. And we can finally look at the full pipeline that we've created. What was it called? Asked NDVI. There we go. So setting up this WMS server manually with tools takes a lot of effort. If you've ever had to do it yourself, I think that you'll agree with what I'm saying. It's quite a bit of effort to get it working. So that was the live demonstration. Now I want to show you a application that we built on top of this technology. So this is a drought monitor. What we did here is we took the soil moisture active passive sensor from NASA. We staged the data on the cloud because it's not available on the cloud yet. What you see here is a static website. So this is just HTML. We threw it on S3. And then the WMS is computed using a Lambda function as well with the same kind of RESTful API. It takes a minute to warm up. Then we computed these statistical drought categories for different levels of drought, abnormally dry through extreme drought. This was a huge computation. We used the Lambda functions for that as well. And so then what we can do is we can take the current soil moisture data from the SMAP satellite sensor and categorize it. It's a little bit easier to see on the time series. So this is again comparing the National Drought Monitor in the US. These are the categories that we compute. And you can see the different categories. It's a little bit easier to look at the soil moisture. So this is the soil moisture coming from the SMAP sensor. And then you can see the categories change over time, depending on the region and the climatology or the statistics of the history of the soil moisture as measured by the SMAP sensor. Okay. As a note, so the drought categories for the world took, it's 5 years of data. We ran 800 Lambda functions continuously, and it cost us about 1.2K. So yeah, you can run up a bill pretty quickly on AWS, so something to be aware of. But it's also impressive that it only took us a day to do this huge computation. So where we're heading next, we're trying to make this even easier for people to use. So we're working on UIs. This is an example where the automated harmonization really helps out to look at different data sets and compare them. So what I have here is I have Cosmos sensor, and I'm plotting it on its own lat-long coordinates. I can also plot it on its time coordinates, and I can plot it as a scatter plot, comparing different channels of the same sensor. So I'm looking at the correlation between neutron counts and pressure. Okay, so that's great, but it's a single data set. It'd be great if I can also, for example, plot vegetation. So the vegetation has a completely different coordinate system, but I'm automatically interpolating it using nearest neighbor onto my Cosmos lat-long coordinates. It also works for time. And then I can look at different data sets as well. So SMAP, for example, I can look at the SMAP soil moisture on the Cosmos time axis. And then I can look at SMAP soil moisture on the vegetation axis, for example, using nearest neighbor interpolation or bilinear interpolation. So you can really mix and match between data sets and coordinates in a very rapid way to analyze the data and look at it. So to summarize, PODPAC makes it easy to access data in a unified manner. It harmonizes data automatically. You can transition analyses to the cloud for both on-demand and large-scale computations. So we think it's a very useful library. We'd love to have more people use it. If you want to talk to us about PODPAC more, you can find us online. Feel free to email me directly. This presentation we will put up on our GitHub page, which you'll be able to find there. And if you wanted to contribute, wrapping more data sets would be great. When we submitted this talk, we had basically terrain data sets and SMAP and Cosmos wrapped. And so since then, we have MODIS, Landsat, and Sentinel added to the family. We spent a lot of time with in the guts of PODPAC, but now we can really work on making applications and wrapping these data sets. And I also want to acknowledge our funding sources to develop the software. So thank you very much for your time, and I look forward to answering questions.